Let's get it started in here.
In this section, we're going to go over summation notation. Remember we talked about in the previous lesson that we use summation to express sums compactly. So if I have the sum from k equals 1 to n of a sub k, that means you plug in 1 all the way up to n in for the formula that you're given, 1 and then 2 and then 3, all the way up to the n, and you're going to add up the stuff in the middle. So this is a capital sigma. K is called the index of summation, or the summation variable. 1 and n are the extreme values of that summation variable. Now this summation variable, this k, can be the letters I, j, or any letter you want. I'm going to use k throughout this assignment. So what I'm going to do now is show you in example 1 how to evaluate a summation given an equation. So for this example, what I want you to do is evaluate this summation. So the sigma is how you know you need a summation. Your summation variable, or your index of summation, is k. So our variable here are these k's. And what this notation means is that you're going to plug in the numbers 1, 2, 3, and 4 into this summation equation and then add up your results. So you're going to start with the number 1. You plug in 1 for all of those k's. So this is equivalent to 1 squared, 1 minus 3. You're going to add that to what you get when you plug in 2 for all the k's. So that'll be 2 squared times 2 minus 3. You're going to add that to what happens when you plug in 3 next. So you're going to plug in 3 squared, 3 minus 3. And then last you're going to plug in 4. So that's 4 squared, 4 minus 3. And now you're going to evaluate each of these. So this is equal to 1 times negative 2, plus 2 squared is 4 times negative 1, 3 squared, 9 times 0, that'll cancel that term, plus 16 times 1. So you're left with negative 2 minus 4 plus 16, which means that your answer is 10. So when I ask you for the summation from k is 1 to 4 of this equation, I'm asking you to plug in the numbers 1, 2, 3, and 4 individually in for the k's and add up your result. Remember, when you're doing summations, you're only doing every integer from the bottom number to the top number. Now that you know how to do summations by plugging numbers in one by one and adding them all up, we do have some shortcuts. Everything has some shortcuts. So here are some properties of summations. If I have the summation of a number, all you have to do is take whatever number is on top, your n, and multiply it by the number inside the sigma. You're allowed to break up sigmas over addition, and then down here, subtraction. So you basically can distribute the sigma, just like when we did limits. You're allowed to break them up. If there is a number in front of your equation, like a coefficient, you can pull coefficients to the front of the sigma. So that's why this coefficient is on the outside and the sigma is in parentheses. Now you also have shortcuts for some formulas, or you have some formulas for shortcuts rather. And these formulas basically allow you to plug things in for the k's you saw in example 1 so that you don't have to add them up individually. If you just have a plain k, all you have to do, instead of adding 1 plus 2 plus 3 plus 4 all the way up until you get to the top number, is plug the top number in for the ends. The same thing if you have a k squared in the problem. Instead of doing 1 squared plus 2 squared plus 3 squared all the way up into the last number at the top squared and adding them all up, all you have to do is take whatever that top number is and plug it in for these ends. And then the last formula we have to worry about is for cubed. And again, instead of 1 cubed plus 2 cubed plus 3 cubed all the way up into the top number, you just plug in the n, the top number, into this formula and get your solution. I'm going to show you an example of how to use these formulas. You're going to have to turn the page in your notes. And I just want to make sure that you understand you do not need to memorize these formulas. If you need them at any point between now and the AP exam, even on the AP exam, they will be given to you. You just need to know how to use them. Let's look at that now. So here's some examples that I'm going to do to show you how to use the formulas on the previous page. In that first example, the summation from 1 to 100 of k means I want you to plug the numbers 1 to 100 in for that k, which will pretty much turn into 1 plus 2 plus 3 plus 4 all the way up to 100. And you could type that into your calculator, but it's going to take you a long time. With the formulas on the previous page, all you have to do is plug the top number in for all of the n's. So 100 is our n, and our formula, when it's just a plain k, is n times n plus 1 over 2. So when you plug that in, it's just going to give you 100 times 100 plus 1 over 2. And that's easy to type into the calculator one shot. It gives you 5050. Now it becomes even harder when I add powers to the k's or to the formulas. The second one, I give you 1 to 20 with k squared now. That means I want you to plug in the numbers 1 to 20, square them, and add them all up. 1 squared plus 2 squared plus 3 squared plus 4 squared. You could type all these into your calculator and add, or plug the 20 into the formula on the previous page of your notes for the k squared formula, plug that in for n. And that formula is n times n plus 1 times 2n plus 1 over 6. So that'll be 20 times, I am using my notes, 20 times 20 plus 1, 2 times 20 plus 1, that's all multiplied out, all over 6. And again, that's a lot easier to type into your calculator, and you get 2870. So that's a lot faster when you know the formulas. And again, remember we're going to use these for Riemann sums and rectangle stuff in a few minutes. Now when I get down to a problem that you're going to see, like example 3, here the top number is just n. And you're allowed to go ahead and add these things and subtract these things individually, like I talked about in the properties a few minutes ago. So I'm basically going to plug n into the formula for k squared, k, and then the 3 has its own property that you saw on the previous page. So for this k squared, I'm going to plug n in to the formula. So just basically copying the formula we just did, n times n plus 1 times 2n plus 1 over 6. So I just replaced this k squared. Now, constants can move to the front of sigma. So this minus 4, I just copy that down. And then here's a k, so I now need the formula for k, which is n times n plus 1 over 2. And then the property, when it's a plain number by itself, is that you just multiply this n times that 3. So at the end, you'll have a plus 3n. So basically, you can do a whole bunch of algebra, and through the magic of algebra, I won't waste your time writing all that out. You have to get a common denominator, FOIL this, distribute. So do some algebra. You guys are good at that by now. And you're going to get, I'm going to copy this off my notes I have in front of me, 1/3 n cubed plus 3/2 n squared. Oh, I'm sorry. It's a minus. You know me with these videos. Just keep going. And then plus 7 over 6 n. And then that formula you could use depending on what n was. So this problem is made a lot easier for multiple values of n. I can make n any number I want. And what n represents is going to be important in a little while. Make n any number I want and then just plug it into this formula, as opposed to going ahead and taking the numbers 1 to whatever number this is, plugging it into this formula, and adding it like we did in example 1. Now that you know how to use summations and summation notation and the summation properties and formulas, I want to talk a little bit about how we're going to use these in terms of integrals, in terms of rectangles. We're going to go over this a little bit more in class when I see you next, but it would be really helpful if you would watch this, try to understand it, take as many notes as you can, and come prepared with questions. Now, since we know that the definite integral is the area under a curve between 2 points, so from here to here, this area that's shaded from A to B, we can further apply this notation, summation notation, to adding up all those rectangles we've talked about. Now, for this explanation, our rectangles will all have the same base, but we will not specify the number of rectangles. And what I'm going to do is make the width of those rectangles smaller and smaller. Think about that, smaller and smaller, so small. Yeah, you know where I'm going with that. we're going to make them smaller and smaller so that as they get smaller, we're going to get a better estimate of the area under the curve. We're going to call the width delta x. So you can see down here, I have a bunch of rectangles. Rectangle 1, rectangle 2, rectangle 3, and then my last rectangle. Now for the picture, I know there's a finite amount of them, but I'm not going to specify if you have a finite amount. So we're going to say there are n rectangles. So here's the last one. It's my nth. And then I'm going to pick a random rectangle. This rectangle, I'm going to call it rectangle K. That's the general rectangle that I'm going to use to model all of the rectangle. It's like the representative. Now for each of these rectangles, the base, okay, so from like here to here and from here to here, that's the base of the rectangle, the width, delta x. You're going to take b minus a and divide by n to calculate how much that is. So b is your last number, a is your first number, and then n is your number of rectangles. Like right now, we don't know what n is, so if I gave you like 4 rectangles, n would be 4. But since we don't know, we're going to leave it as an n. Now what we're going to need to do is find the area of all of these rectangles and add them up. So once we find the base, we now need to find the height. So like we've been doing in class, I need an x value to plug into the equation for this line to get the height. Well, if you remember, I have to specify which x value you use. Now we are going to call that value x sub k. So I'm going to talk about this kth rectangle, and I'm going to talk in here, and I'm going to say that you're going to use x sub k and plug that into the function. Your choices are the left endpoint, so that would be this one. The right endpoint, that would be this one. A midpoint, right there. Or some point randomly along this line. Now I know it looks like we're picking the left because I'm touching the left here. But again, this is representative, and I could change the shape of these rectangles and make them skinnier or move them around. If we choose any of those spaces, and we're going to go ahead and make delta x, the distance between here and here, smaller, it's going to go to 0. Basically, the left, right, and middle or random endpoint kind of end up being the same choice. They all collide into each other. So what exactly is that x sub k? What am I going to plug into the function? Delta x is easy to calculate. It's b minus a over n. Those are all going to be numbers, or they're very simple letters to keep track of. But this random x that I'm going to use to get the height, I have to figure out what it is. We'll go over how to get delta x tomorrow, or sorry, x sub k tomorrow when I see you in class. But think about what's happening in this problem. As I added in these delta x's on the bottom, they're in orange, I hope you can see them, I'm basically going from a and adding on delta x. And I get a new spot. This is a delta x. Then I add it on again. So it's a delta x, or a plus delta x, plus another delta x, plus another delta x. What we're going to talk about tomorrow is how I add on these delta x's to get to x sub k. So start thinking about that for our next class. The other thing I want you to think about is what is going to happen to n, the number of rectangles, as I make delta x smaller, as I make it approach 0. What is n, the number of rectangles, going to approach? So think about all of those things so you're prepared for our next class. Be ready to use summation notation with the formulas and from scratch by plugging the numbers in by hand. And how do I find out what x sub k is? What is happening to n as I make the base of the rectangle smaller and smaller? And we'll talk about all of that next class.